Okay, good morning, everyone. Welcome to ME Graduate Seminar. And today it's my great honor to introduce Dr. Juner Zhu. And Dr. Zhu is a research scientist working jointly in the departments of mechanical engineering and chemical engineering at MIT. He received his PhD degree from MIT Mechanical Engineering in 2019, and he got his bachelor and master's degrees from Tsinghua University, where he graduated with the top honor, the Presidential Scholarship for Tsinghua graduate students in 2012. So without further ado, I'll pass the floor to Dr. Zhu, and thank you very much.
Oh, thank you, Yihao, for your introduction and for inviting me. And also I want to thank Zhu for inviting me as well. And hello, everyone. Good morning. I'm your neighbor. My name is Juner Zhu, and as I explained, I'm now currently a research scientist at MIT, and I'm jointly working in mechanical engineering with Professor Tom Wisbicki, and in chemical engineering with Professor Martin Mazant. And yeah, and I'm also the title as Executive Director of the MIT Industry Battery Consortium, because I and Professor Tom Wisbicki jointly developed this program, the current 3-year new phase. And today the presentation, my presentation will be about intelligent data physics integration for characterizing electro-chemo-mechanical systems. So briefly, something introduction about my research activities at MIT. And as I just explained, I co-developed this industry battery consortium with Professor Tom Wisbicki, who is actually my PhD advisor. And we are now developing new CAE tools for battery safety. Currently, we are being supported by 8 companies, as we're really a very wide application covering from battery manufacturers, EV manufacturer makers, and consumer electronic makers, actually. And in the past, actually, this program had been here for about 10 years. We have also some other sponsors over the past decade. And during my postdoc and research scientist career, I joined also the data-driven design of battery center, which is organized, being run by Professor Martin Mazant in chemical engineering. And our task is to do battery degradation modeling and lifetime prognostics prediction. And these are the 2 main research tasks or main centers that I'm involved in. And besides me, and I'm currently leading a small team of 2 postdocs and 1 master student. And we are also working for the NASA project, a NASA project on solid-state batteries using machine learning tools to do interfacial failure in solid-state batteries. And we also have some internal funding, MIT internal funding from Indonesia to do also solid-state battery modeling. Okay, so today my talk will be a lot of work in my talk will be actually the contribution of our whole team on batteries and other solid-state batteries. Yeah, so let's start. Let's say, what is an electro-chemo-mechanical system? Actually, your smartphone is definitely a good example. You may have noticed that there is a number called battery health or maximum capacity in your iPhone. So that number, what does this number mean? Actually, there is a name for it, which is called state of health. So it is simply the ratio between the current battery capacity over the initial capacity that when you bought your iPhone. So that number actually is a result of electro-chemo-mechanical system. Inside the battery, during charge discharge, for example, during the first cycle or the 50th cycle, you will see a lot of particle level cracks. So in this example, actually, we can see electrochemistry and the mechanics are interacting with each other. So in this case, electrochemical chemical performance procedures happens first and induce some cracks at the particle level. And the particle level cracks are definitely mechanics and creates new interfaces and side reactions to deform, make platform for chemical performance procedures to happen. And another example of electrochemomechanical system is electric vehicles. So you must have seen, I guess you must have seen this famous photo in Hotlines. So it is about a burning Tesla, which is, I think, in 2013. And what happened to that Tesla car, Tesla Model S? Actually, according to their report, one of such a tow hook from another truck hit the bottom of the Tesla car, and several batteries deformed, severely damaged, causing electric short circuit and thermal runaway. So in this case, it's also mechanics and the electrochemistry interaction with each other. In this case, mechanical deformation happens first, and deformation induces short circuit, and there are side reactions of electrochemistry, and it causes thermal events and uncontrollable thermal events called thermal runaway. It can also goes back to mechanics, like thermal events and other like severe large deformation of batteries. So again, in this case, it is the interaction. Okay, so from these two cases, I think you must have a feeling that both cases are dealing with batteries. So that's actually one of my key research interests. But this kind of system is very complex. So there are three sources of complexity of let's say electrochemo-mechanical systems. The first one is multiple scales. Again, I'm using a battery, the battery system as an example. So in the batteries, there are multiple scales, let's say from nanoscale of the interfaces. This is one single particle, and that's a lot of particles, electrode, we usually call it microscale, and mesoscale battery components inside one battery, and cell level, and also goes to the macro level, battery modules, put all the batteries together, like battery modules, battery packs, and transportation. Transportation is very well known as a complex system, and you can see a lot of scales here. And the second source of complexity is multiple materials, phases, and physics. And just to name a few, for example, at particle level, you may see phase separation during charge discharge. One single particle is not charged uniformly, so which is called phase separation. And at electrode level, we can clearly define electrochemistry, and mechanical wise, we have plasticity of granular materials. It can flow. So this is another physics that we want to look at. There are much more. So it's definitely a multi-physics problem. And third complexity is usually called curse of dimensionality in data science. So that means the complexity of the whole system increases exponentially with the number of variables and degrees of freedom. Just to give you a feeling, so our team is not able to develop FEE models at different scales at each scale. However, it is very hard for us to develop one uniform model because of this curse of dimensionality. So today I will show you a real world example how this curse of dimensionality is limiting us. Okay, so as I said, these systems are usually complex. So what is the fundamental challenge if we want to characterize this system, or we want to engineer such kind of systems? To me, in my vision, the fundamental challenge here is the trade-off between physics and data. So as I just give you some examples of physics, you can see a lot of physics can be defined in this range, the small range, or the nanoscale and microscale. And that's actually usually what we observe. So physical laws can usually be clearly defined, written down at small scales. However, at macro scales, for example, car level, this kind of physical laws are usually hidden, cannot be seen easily. However, the good news is at macro scale, we have more and more data, and big data is now a very hot area. And big data from EV, it's being talked about every day. The good news is big data generation and big data storage is now kind of affordable to us. So data is big and affordable. However, at micro scale, data are usually small and expensive. Just take one example of this particle. So this one single image took my colleagues at NREL like one month to obtain such a single photo of one single particle. So that's actually a lot of effort, which I mean the data is expensive. Okay, so my methodology of studying this kind of complex engineered systems has three aspects. At micro scale, we learn electrochemomechanics or physics from small experimental data, because here physics can be written down clearly, but data is small. So we want to make full use of the data. And at micro scale, we develop data-driven health and safety prognostics for the complex systems, for the complex engineered systems. And in the mesoscale, the wide range, we develop multi-scale and multi-physics computational models. So these three aspects actually are connected with each other. Usually, if we learn like physics first at microscale or nanoscale, and we implement it into a model and use a model to do a model-based like prognostics, that's a traditional physics-based roadmap. Physics here and predictions at large scale. There are some other ways to do this. If we have a lot of data, we can do data-driven first and get the trend, and we can guide the design of computational models. And these models can predict mechanisms at small level. So this is a typical data-driven approach. So that actually goes back to the title of my talk. How to combine data-driven method with physics-based roadmap is a big challenge that we want to look into. And in today's talk, I will give you two examples to show how these two are interacting with each other and how to find the balance between these two. Okay, the first part is actually from mesoscale to microscale, which is implementing some physics into computational models of porous electrodes and the battery cell. Okay, so before that, let's think about talk more about what will be a lithium-ion battery cell, or what can be modeled for a lithium battery cell. So actually now in the commercial, like the market, there are different kinds of batteries. You can see a lot. For example, cylindrical batteries has been used by Tesla for quite a long time. And this kind of prismatic cells is now being used by many cars. For example, LG Chem developed this kind of batteries, and Samsung developed this kind of batteries. For GM, Ford, they all use this kind of batteries. And pouch cells, probably you can easily find it in your cell phone. So pouch, there are different kinds called form factors. But in terms of structure, the basic structure, fundamental structure are really very similar. So this is the solid skeleton of one unit cell. Let's say RVE, smallest representative volume element. So in one smallest unit, there is let's say cathode and anode, which are two electrodes, and usually those particles are touched on metal foils, acting as current collectors. And between anode and cathode, the two electrodes, there is separator, usually polymer, porous polymer. So this is the structure. And of course, all the solid materials in the commercial lithium batteries are saturated in a liquid electrolyte. And during charge discharge, there will be mass transfer and also the transfer of electrons. So there is electrochemistry. So with this understanding, actually, we can write down an equation. Let's say battery modeling equation. So a lithium-ion battery model, there are three parts. One is the mechanics, let's say solid mechanics of layered porous media. And we need to know flow of liquid electrolyte plus electrochemistry. So you can see a lot of physics here already. And let's, in the first part, I will use this equation a lot to show you how I will develop the model. So let's start from the mechanics of layered porous media. Let's say to really develop a good model for this solid skeleton, we have to test a lot. We have test all the components. So there is a fancy word called learning. So we have to learn mechanics from the component level test. So our team has been working on this actually for, let's say, 10 years. So our team has almost tested everything, like polymer separator. We did reconstruction of the polymer, and we did tensile tests for polymer, the separator. And we also tested, for example, the shell casing, the enclosure of the battery. And we also tested the current collector, which is the metal, the aluminum, and the copper foils. And recently, I and my collaborators tested the active granular material. Actually, this is a core material in this battery system because this is where the reactions happen, the interfaces. So with this testing, actually, we can calibrate models and implement these mechanics into the RVE, the smallest unit cell. And this is something what we developed. It's a cross-section of a model. We simply put layers together and give the mechanics into each layer. I mean, this kind of model, the smallest unit is like this. And each layer means each component material, and we give the constitutive laws into each material. And this is a simulation result of we call it indentation. This is the indenter, it's a rigid indenter, and the battery layered structure deformed in this way. We can see clearly like there is here strain localization, which is very interesting. And also the force we can measure, for example, the force and the displacement of this rigid indenter. And here are the black curve is the test that we did on batteries, and the blue dots are simulation results. We can see a quite good prediction of the trend, overall trend. There are some overshooting here, but that's because of the element deletion in the finite element model. So if we look at this moment and cut the battery to see like the cross section, and we can see clearly there is a very interesting X-shape fracture, and our model can definitely predict this. So this is a very, actually to us, it's a very exciting achievement about the solid skeleton. That means our solid skeleton mechanics is very well captured, and we are ready to combine this solid skeleton mechanics with other effects. For example, electrolyte. So what will be the electrolyte contribution? That's actually one possibility. If we do an indentation test, we will see electrolyte being squeezed into the neighboring parts instead of this localized region. So there will be definitely deformation-driven flow of the liquid electrolyte. To validate this effect, actually, we performed several uniaxial compression tests on the solid skeleton. So we did 5 different loading speeds of the compression test on this unit cell, and we measured the nominal stress strain curve. We can see the dry material, which is actually, the curves are almost identical. That means there is no contribution from the electrolyte. However, if we do a saturated porous media with electrolyte, we see clearly there is a strain rate effect or speed or dynamic effect. And we put the dry curve here. That means at a very low speed, the dry and the wet curve are the same. So in order to capture this phenomenon, actually let's revisit the battery modeling equation. So we have the mechanics of solid. We gave it a simple, quite simplified model of mechanical model of to capture the flow of electrolyte. Here is a part, two simple equations here for a part of the equations here to just give you an example. So how we update the stress, and we use the Darcy's law to capture the flow in porous media. And there are much more, and I am not listing here, but simply put these two together can give us some very good results. For example, for some simple geometry, for example, uniaxial compression. Here, this is the dashed lines here in this picture is what we obtain analytically. We have very good, very accurate predictions of the strain rate effect. However, if we want to extend it to more complex geometry, I have to say, if we use computation, the computation in ABAX or software just about it cannot continue to give us a very good result. Okay, and how about electrochemistry? So there is as I just said, in real world, during charge discharge, there will be electrochemistry. And one simple example is diffusion, right? There will be diffusion. And the state of charge, that means how much of the battery is charged, and kind of how much lithium goes to stored in the anode side. And this is the battery. During charge discharge, the battery, the thickness will, one clear observation is the thickness of the cell will change So we use the DIC digital image correlation method to measure the thickness change of the battery, and we see that during like state of charge 30% state of charge, there is almost no deformation yet. However, during 100 at 100% of charge, we see a severe like displacement field. So how to model this kind of thickness change of the battery cell? This is a task for us, and we now implement some diffusion equations into the solid mechanics model. And again, this is part of the physics here, part of the equations here. The decomposition of the total strain is elastic, plastic, and the diffusion-induced strain. And the diffusion-induced strain is correlated with the concentration of the lithium ion in different layers. So in this way, we can give predictions. So here are the predictions. The x-axis is time during charge discharge. This is one charge discharge. Another, I showed 5 charges. So the gray dots are the SOC, state of charge, and the blue and the red curves are the displacement curve. So you can see during charge discharge, the thickness of the battery is changing, and the red is experimental, and the blue is our model prediction. So overall, the trend is good. However, there are a lot of let's say deviations between experimental and model. So let's say the prediction is satisfactory, considering that our diffusion model is quite simple, and the model is basically 1D. So the prediction is understandable. The error here, we know where it comes from. However, if we want to extend the model to cell level, to the whole battery cell, again, the computation aborted. We cannot continue the computation. Okay, these are 2 examples like how we put more and more physics into our mechanical model. And here are the summary. Let's put a very short summary here, revisit this equation. The battery model equals mechanics plus flow fluid and electrochemistry. And we just showed that in the first, the mechanics part, we show that our mechanical model works perfectly. However, once we add more and more physics, it sometimes works, but in a very simplified cases, it works. However, the more we add, the more difficult the computation will be. So that's exactly what we mentioned, like the curse of dimensionality. There are more and more dimensions, freedoms of degrees of freedom, and also other variables. So the computation task will be very difficult. So think about, we put everything together, even it's a simple diffusion equation or a simple flow equation, that will make the case even more complicated. So we can anticipate that there is actually no way to do such a high dimensional computational model that capture everything with our current current computational capability. So that is clearly a very daunting task for us. So we started to think about if we can replace some of the modeling work with, for example, sub-models, independent sub-models, because you see most of the complexity till now comes from the mechanics side. Can we put it as a surrogate model? Let's say an analytical model. For example, in the past, some people developed this kind of analytical model to fit the stress strain curve of this kind of unit, so that in our multi-physics model, we don't need to calculate every time to calculate this unit cell. We just use one equation to calibrate this. However, the reality is this kind of structure is already very complicated. So we start to think about if we can make use of the recently very hot area, let's say data-driven method or data science method, neural networks. Can we use a neural network to represent the mechanics of this layered structure? That's definitely doable. That's something what we did. We use this RVE to generate 1,000 of loading conditions. There are 1,000 loading paths into this RVE, and that means we give it a string and we measure the stress in the 3D space, sigma 11, sigma 22, sigma 33. In this way, we have the stress strain relation, 1,000 histories, and we trained a neural network to help us capture this stress strain relation. So this is actually the recent work of my colleagues. So we developed two GRUs with 200 neurons, and two hidden layers and 200 neurons. That's actually a lot of parameters, 440K parameters. That's actually a daunting number, I think. But anyway, we figured out and we trained this long short-term memory unit to help us to directly bypass the calculation of RVE and directly predict stress from strain. And clearly there is some advantage. It's like now we are able to store all the mechanical constitutive relations into one equation. The straight curve can be trained independently. We don't need to calculate in the multiphysics model now. And it serves as a lookup table for the overall battery model. That's the advantage. And the biggest advantage is the computation cost of the solid mechanics part is greatly simplified in the like after training. So the training procedure has still a lot of work, but during use it is much reduced, smaller computation cost. Okay, then actually let's look at how powerful this neural network is performing. So actually, in my view, it is just a high order nonlinear equation. Let's see here. We compared, for example, use a 4-parameter previously established analytical model to fit the stress strain of the layer structure. It performs very poorly actually because that's only 4 parameters, and the dashed line at the model and the solid line as the line as the RVE performance. It basically failed to capture the trend. However, with the neural network, actually we can capture almost perfectly the RVE performance. So that's the advantage of so many parameters. Okay, and there are still challenges. So although it is a curve fitting, mostly a curve fitting task, there are the challenges how to find the right best network to capture our RVE performance. And another challenge is how to generate such a big data. So only mechanics is still fine because we can run a lot of simulations at the same time, and there will be quite easy to process. However, if we have now another physics, let's say flow of fluid adding into the RVE, we definitely don't want to do so many simulations. So the previous, like the example, in that example, we only use neural networks as a data-driven method, purely data-driven model. So we depend on big data and to give us output. However, when sometimes we cannot do so many simulations, so we still start to think, can we make use of another method? For example, so what else we have is physics, right? We know part of the physics, for example, the flow of electron. We know the equation. Can we put the equation into the neural network model so that it becomes so-called physics-informed neural network model? So in this way, we will not depend on such a big data. Of course, I'm not the first guy to think of such a method. There are already some other researchers have this kind of similar ideas. So one of the ideas physics from neural networks. So for example, I think Rice's paper probably is one of the first who used the idea of physics from neural network, or PIN, to solve the Navier-Stokes equation for incompressive flow. So this is their example, and they can predict, for example, the pressure field of their flow. And recently, Lulu's work at Brown, now currently at UPenn, actually he developed even a library how to use this kind of PIN to solve different equations, for example, diffusion equation. So actually the logic here is quite simple to all of us. So we use just a neural network to represent the solution of this equation. So the x and t are the two parameters, variables that are independent variables, and u is the solution. So we use the neural network to represent the solution, approximate the solution, and we put the PDEs and the boundary and the initial conditions into the loss function. By minimizing the loss function, we can get the prediction of, the parameter of the neural network, also the solution of the equation. So that's how this physics-informed neural networks work. It's more like a solver, a PDE solver. And we started to think, can we use this kind of pin to help us solve some solid mechanics problems? Because previously successful models are basically in fluid mechanics and mass transfer. So we started to use it for solid mechanics, and our team successfully developed two methods. One is PDE based, which is actually pin, and another is energy based. For example, we minimize the total energy of the system, potential energy of the system. In some cases, for example, elastic plate, it works perfectly. So there are two different ways to define your loss function. Here you can see, here this is a prediction. We compare the prediction, PDE-based and energy-based, with our simulation, FE simulation. This is one case of a non-uniform tensor test. So PDE-based model, I just forgot to mention that there is a parameter called weight, the weight factor. So a lot of effort should be used to optimize this weight function or weight factor to get your result. So this is a painful thing of the PDE-based. However, the energy-based, there is no such a thing, because the W actually is determined based on energy, potential energy. So, for example, in this simple case, the simpler case, the predictions of the both method as good as FE simulation. However, if we introduce a Hall into the center, we will see that PDE-based is really struggling to get converged by this W. But if this is only 30 numbers of iteration, if we can continue more and more, we will definitely get the correct result, but that's a lot of computation result. So I just show you these 30 iterations. Energy-based simulation loss function actually works perfectly. And we also even push it more to the limit. We introduce 3 holes. So energy-based again work perfectly. However, the PD-based struggled to get it, but the trend is good. And we also try to put more iterations of W, and we get it. So that means PDE-based usually need more iterations. However, energy-based is more efficient. However, energy-based has a limitation because not many systems have potential energy, minimizing potential energy principle, right? So we will later see this. And then now we have so much knowledge in how to use the physics-informed neural network. We want to apply this to this structure-fluid interaction in batteries. So again, now we can construct a neural network to approximate the solution of our system. So the equations, the variables here are the coordinates and time, and the output is the displacement field and the pressure of the fluid. Here, the known physics here is the mechanics of solid phase, and we have the flow of electrolyte. As I just said, the equations are all known to us. So it can help us to minimize by minimizing the loss function, we can predict, for example, the pressure field. You can see the prediction is quite good for our local indentation. And we also try to compare this pin prediction with our FE simulation. So in this system, in this case, there is no minimizing potential energy. So we have to use pin to solve equations. So the prediction are quite good after a lot of iterations. And we accurately predict the pressure profile over the X position. Okay, of this actually here is the thickness direction. Okay, so this actually is what's our current status of our research in this part of multiphysics and multi-scale modeling. So the key takeaways here are that actually I showed that multi-scale and multiphysics models suffer from curse of dimensionality, and the neural networks based on RVE is very useful to store some stress-strain relations, and this kind of physics-informed neural network or PIN can be used to store some physical laws, right? So it will be more exciting to combine these two kinds of neural networks. This is our ongoing work, of course. And as I just mentioned, energy-based PIN seems to have very powerful application, more efficient application to minimizing, for example, if the system have free energy and definition. So for example, the phase field fracture. So this is another project that we are working on, and we already have some very preliminary results to show for example, the phase field fracture in such a central host specimen. And I will leave this to the future. Okay. And in the second part, I want to talk about that if there is a system that or a material that the physics or the mechanics is unknown to us, how can we make use of computer algorithms to help us learn the physics? Here, I will give you an example of pure lithium. So why pure lithium? That's because nowadays, today's lithium-ion battery cells, as I just showed you, the cylindrical cells and prismatic cells, all are approaching their upper limit of the energy density at cell level. So with this current level of energy density, we can definitely to develop like Tesla cars. This probably is one of the biggest range that human engineers has achieved, 400 miles electric vehicle, just announced last year, I think. And with these cells, it is also possible to develop like electric flight, but this is really experimental. It also took first flight last year designed by NASA, Maxwell series. This is X57. And if we want to extend the success of this kind of application, electrification, to future, like let's say commercial airplanes, the challenge is still on the battery side. So people are now thinking to increase the current the energy density of the batteries. One way is to replace the graphite anode with a lithium metal anode. So there's a lot of research going on lithium metal anode. So either solid state batteries or lithium metal anode, it is very important for us to understand the mechanical property or the electrochemo-mechanical property of lithium metal. So that's why we started to look into the lithium mechanics. And here are some current existing research. So in this plot, I show you the x-axis is the length scale that the experimental experiments were performed, and the y-axis is the yield stress. So a lot of studies have been performed in this range and in the bulk range. So, for example, recently, very excitingly, there is a recent paper in Nature Nanotechnology, a group led by Georgia Tech. They performed very exciting small nanoscale compression of pillars of whiskers, lithium whiskers, so that they had actually intended this plot to this range, nano range. So we now have a better understanding of this trend. However, we can still see there is a gap. So the micro to mesoscale, there is a gap to do this, to understand the lithium mechanics. So that's the motivation of this study. We want to give this gap because as this gap is very important, the thickness of the lithium metal inside the cell is in this range. And the lithium surface roughness is also in this range. A lot of things fall in this range, and we must have a lithium mechanics model for this. Okay. Now, as I said, the lithium metal mechanics in this range is unknown. However, what we know is the general mechanical framework. Let's say this is a metal material. So we can guess that we can apply the general continuum level constitutive equation to this lithium metal. These are two key equations. This is called the yield function. It is basically the function of stress and strain. And strain rate. So this is the very general form, and there are unknown parameters, coefficient. So let's assume that every parameter is unknown. So how can we learn this mechanics? Human brains are very good at learning. So we usually control variables. For example, we do uniaxial tensor test. In this test, there is only one non-zero term. So it is constant rate and gradient free. We plug this stress into this model, and we will simplify everything, like other parameters are just gone, and we can learn one parameter each time. So this is a very comfortable way for our human brain to learn all the models. Of course, now we have computer algorithms. Computer algorithms are very good at sensitivity analysis of multiple variables. So we now can develop a complex material test, and in this test, none of the parameter, the stress components is zero, are zero. So we can plug this in. However, it will not help us to simplify this. What we can do is simulation. We can measure the force field strain in this test. Experimentally, we can also do simulation and predict it, and then compare these two. When we minimize this, the prediction, the deviation, the loss function, we can actually, in a way, we learned multiple coefficient at one time through inverse method. So that's what we mean that we can help you make use of computer algorithms to help us better learn mechanics. So this kind of inverse learning algorithm, we expect that it can be very powerful when the testing cost is very, let's say, testing is very expensive. For example, synchrotron, we can usually do one-day test every year. So then we want to just do one test and learn everything. We don't want to repeat a lot of tests. So that's the advantage of computer algorithms. Okay, so we started to develop this inverse method and apply this to lithium plasticity. So this is, for example, one test that we can do, and we measure the force. When we do the tensile test, we can measure the force, which is integral of the stress in one cross section, and we can use image data to measure the force field displacement. Then we put it into the inverse learning algorithm. We put, for example, we already know the general quadratic U function and Harding law. We put the initial guess into it, and we design a plasticity subroutine and use FE model to solve it. And we gave stress and strain field in the simulation. And there are two residuals, force-based. We can compare the force simulation and the experimental. We can, more importantly, we can compare the strain-based residual so that we can minimize it and get the learned physics here, learned mechanics here. So here are the, so now we have the algorithm. So where the data comes from, it's another important thing. So a very smart master student in our lab developed safe laser cutting technology, which is very challenging because lithium is very active. So this master student helped us to develop this very simple but powerful tool to laser cut thin lithium. And he designed a chamber, and in this way, you can see we can test very, very tiny samples of pure lithium. And here are the test results. We designed 5 different loading conditions, and all these tests are performed under a camera so that we can capture the strain field. Is it playing? Oh, sorry. Okay, yeah, so we can see there is a strain localization in each test, and see the fracture clearly. Yeah, with the help of the DIC system. And then we apply all the data into the algorithm, and we inversely get the prediction of each single test: central hole, notch tension, different notch tension, simple shear, and uniaxial tension. So we use 4 of this as training, and we used one uniaxial tensile test, most simple one, the simplest one, for validation. And then these are what we learned: the A matrix, which stands for anisotropy. Here, very interesting. This is what we learned, and we can, of course, do additional tests to measure this coefficient. These two are very close to each other. More exciting is that we input in the simulation, we put a creeping law, a rate-dependent law, into the material model, and nobody did a creeping test. And we learned the creeping parameter, and this is what has been reported in open literature. These 2 parameters are, again, very close to each other. This shows the power of inverse learning. That means creeping is correctly learned without performing a traditional creeping test. This is the power of the very exciting thing of inverse learning. Okay, and after we learn this lithium mechanics, what can we do? So we developed through a collaboration with University of Houston, Yao's team. We now are working on solid-state batteries, and this is solid electrolyte that we have from the collaboration, and we performed image-based reconstruction. There's a long story in this aspect as well, but I will not go into details. We can reconstruct the microstructure, and we use the microstructure, turn it into FE simulation, and this is a lithium plate, and with our learned physics. And we apply here to mimic the real world like manufacturing procedure. There is usually a control, a displacement control compression, and we do this simulation. This is fixed, and this is displacement control. And the solid electrolyte is a sulfide-based solid electrolyte, and it is elastic plastic, and all the particles can move. Here are simulation results. The two videos here, and one here is, let me see. Okay, yeah. So the video now is playing, and see the lithium is being pushed into solid electrolyte. And here is a cross-sectional video in which we can see the penetration. Okay, it's fine that if it's done to play. So we can see clearly the way how lithium, like a flow, like a fluid, goes into the solid electrolyte. This is what we learned from the creeping and all the rate dependence. And here, this is simulation result after we take the lithium plate out. And we can see clearly there are some penetrations. This kind of penetration is very critical to battery safety because it can cause short circuit. Okay, so here are some summary about part 2 of inverse learning. So I just showed that how efficient that algorithm-assisted inverse learning approach can be applied to lithium mechanics, and we develop experimental data set to help us to train this, to use this algorithm-based inverse learning algorithm. And we also show that the lithium mechanics that been learned can be used to model solid-state batteries. And in the future, we are still looking into, like, because I didn't mention is we make use of optimization method in MATLAB, which is now we are using a Bayesian optimization. As we know that Bayesian optimization is now very powerful and a very hot area for, let's say, for black box based systems. But now we are still just using a small part of Bayesian optimization. So in the future, we will try to make more use of it and to further reduce the experimental cost. And we also want to, currently we're also applying the inverse learning approach to cathode particle model. This is a more complicated structure. And we hope to learn the cathode particle physics and also the interfacial strengths, which are not directly measurable, still unknown to us. Okay, so I think my talk has focused on so much on batteries, and you may feel like why we are talking about so small area. Actually, I want to close my presentation like giving you more real-world examples of chemo-mechanical or electro-chemo-mechanical systems. One of the example is COVID-19, the viruses. So virus endocytosis, how the virus goes into the cell, actually is a typical example of chemo-mechanical. There are chemical potentials outside the cell and inside the cell. To model this mechanical as a system, we have to think about chemomechanics. And a lot of people now are developing electric active materials, for example, to design artificial muscles. So these are some examples that we can use electric signals to control the mechanical deformation. Another very exciting area. And also don't forget large scale. We have, for example, oil reservoir. In the oil reservoir, you can see clearly there are porous media and water, oil, multiphysics at large scales. That's very exciting for us to learn to apply chemomechanical models into this kind of system. So all these systems, you can see that today the methodology that I presented can be used to these systems as well. Okay. At last, I want to thank our team again, and I like this team a lot because we are exactly working like a battery cell. We are one electrode at MIT, and our collaborators another electrode, and we exchange ideas and knowledge. We output model series data, and we serve the community of applied mechanics and applied, let's say, engineering. So that's really exciting to me, and yeah, so thank you for your attention. And if you have any questions, I'm happy to take them. Thank you.
Thank you very much, Dr. Du. And from the audience, if you have any questions, you can unmute yourself and directly ask, or you can also type it in the chat.
Yes, yes.
Thank you, Dr. Zhu. I have a question on the physics-informed neural network. So I was playing around with that specific algorithm myself as well. So I encountered some problem when I'm training the model. As you must know, there are several different tasks in training PINN, which is to satisfy the boundary conditions, initial conditions, and the governing equations, right? So when you are training your PINN, how do you balance out all those terms while training so that all the tasks can be minimized?
Sorry, your balance the which terms? So you mean
so,
can you?
Yeah. Specifically, in this equation, you can see there are the last term has like multiple different equations to satisfy at the same time, right?
Oh yes. I think I got your point because let's go back to that one. This one will be more intuitive, right? So yes, that's a very big challenge. I think the difficulty to use this pin is really painful thing for me as well. So how to balance, how to give the weight function, right? How to give the weight function. Now our team is doing optimization. We simply optimize the parameter, but definitely it's very hard to coordinate all the terms. And in some cases today I didn't show as in some cases boundary condition will fail. So so there is actually some publications from Jianxun Wang's team at Notre Dame. So you can definitely, I think if you are using it, you must know their team. So they have a concept of hard boundary condition and soft boundary condition. So there are algorithms for you to use already. And you can, I would suggest that you look into those publications and how to treat this problem. And in our team, you see, when we apply this pin method to elastic plates, we just simply optimize the energy. That's a much easier way if you would like to see. And if you are working on thermodynamics, I would say I would strongly encourage you to use energy base, so you can bypass a lot of things. And for example, that one I just showed in phase field fracture, so there is a free energy term to minimize. If you have such a term, just use energy base. I think that's my suggestion.
Yeah. Okay. Thank you for that one. I have actually the second and the third question. So sorry for that. Yeah. So the second question is, when you're training a PINN, do you solely use all those collocation points like unsupervised, or do you have more simulation or experimental data to guide you to initialize the model?
So yeah, that's a great point. So that's what we learned, because 2 years ago, we are also new to this area, and we spend a lot our learning curve is super long. And that's why we tried the energy-based. And energy-based, it looks like energy-based is very, as I said, more physical. So actually think about the difference between energy-based and PDE-based. Energy-based, that's just the weight function has some physical meaning, so that your loss function becomes energy, right? So we suggest actually if we can think about the energy terms in each, like that's virtual energy, right? So think about the energy, and if we can use energy to quantify your, let's say to give you the initial guess of this W, that will be a very ideal case, I think.
Yeah, I feel like energy-based functions to just transform all the different terms into one equation may be a good solution to this specific problem. Yes. Yeah, but still, anyways, the third question is, I realized that you are doing some kind of inverse problems in the second part, right? I also remember that in PINN, you can also use PINN to do the inverse problem to find out some of the terms in the equations. So have you ever tried such kind of approach? Is that working?
Exactly. You see here, I didn't mention, because the purpose of our study is not like this. So you can see the prediction here is kind of a way of inverse learning. So the parameters of, let's say here, alpha and the kappa are unknown. So we first train the neural network, and then kind of inverse method to calibrate this data, these parameters. But as I said, the purpose of our study is not use it as a PDE solver. As you can see, as if it is purely a PDE solver. Simulation, FE simulations can do much better. So to us, neural networks, right? Neural network to me is more like a function to store my information. I don't want to use it solve energy. PDEs. I want to put the physics and data into this neural network so that later we can just take this. We don't want to calculate again and again. After training, put it there. That's the big.
Yeah, I see. So if I understand it correctly, you're using such kind of neural networks to store like all those things so that you can minimize the time in calculation and in the cost of like storage and also the training time. Is that correct?
Exactly. For example, this model, right? I really don't want to calculate again and again. Just calculate once, put it there.
I see. Thank you.
Thank you for your questions. Very relevant. Yeah.
All right, great. Cool. Thank you very much, everyone. And this is a wonderful discussion. And as you know, Dr. Zhu is at MIT. It's not far away, 40 minutes. Feel free to definitely reach out to him, and then hopefully you can have more collaboration. So with that, thank you very much again, Dr. Zhu, for your time and this excellent talk. And thank you very much, everyone, for joining. So this is going to be the last seminar for our semester. So in 2 weeks, you're going to be in the final. So we wouldn't have another one. So with that, thank you very much, everyone, and have a great holiday season and good luck with your finals. Then I'll see you in the new year then. All right, so bye now, take care.
Yeah, thank you, Yihao, bye.
Thank you.
Good luck, everyone.